Hi guys, so that's going to be a short video about the simple harmonic motion and a very simple demonstration experiment that you can even do at home because the material is so cheap. So here I have a spring. That spring is not stiff, okay, it's very flexible. So the spring constant should be very small. And here I have a mass. The mass here is 90 grams here. So according to theory, the period is the time for one cycle. So how long it takes to go back, to go up, and then back down. So that's one cycle. So the time for one cycle is the period. And you see, it's proportional to the square root of the total mass here on the holder over the spring constant. So the square root, there is a square root here. So it makes sense because you see, as you increase the mass, you increase the inertia. So that will be the laziness at changing the state of motion. So it means turning around, going up, and then change again, going down. So as you increase the mass, of course, the period is going to increase and the motion will not be as fast. Okay. Also, the period depends on K, the spring constant. If you have a large K, the spring is stiffer and it's going to go up and down quicker. Okay, so you get that when you do Newton's second law. The force applied here is the weight, and then you have a restoring force. So you're going to have an acceleration, you have a differential equation, and you can find that the period is expected to be this. So if you want to do an experiment, a square root is not very convenient. So you square both sides, and you have that the period square should be proportional to the mass. So the unit here, the mass, should be in kilogram, and that, of course, is going to be in a second square. So you expect the proportion between the period square and the mass, right? So linear relationship between them. And it's an experiment that is very easy to do. So you can get your smartphone and try to do it with me if you want. So, of course, one period is too fast. So what we do, we're going to do 10 cycles, 10 oscillations, and find the time for those 10 oscillations when you have 90 grams, right? So I'm going to put it down. So interestingly, in that equation, you don't see the amplitude here. So it doesn't matter by how much I'm going to pull it down. You don't want to pull too much, of course, because it's going to go oscillate in other direction. You don't want that. You want the oscillation to occur vertically. So I'm going to pull it down, and I'm going to count 10 with my phone. So it's going to be 1, 2, 3, 4. Okay, let's start again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh. And usually you have to do it several times, and then you average out because your reaction time is not going to be the same. So you want to do it like 10 times, you average, and you're going to find something like 9.5 seconds. And then you do it again for your increase. So here I have 10 grams. You increase the mass by 10 grams. I'm going to put my 10 grams here. And you're going to pull it down again. A little bit, not too much, right? You're going to see it's going to go slower. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. Right? So you're going to get about 10. I got about 10.5 seconds. Yeah. About. And again, you are supposed to do it several times. or to count, to do it, to find a time several times, and then you average out. So I increase again the mass. So now you should see it's going to be stretched more. So remember the stretch depends on the stress. So I pull it a tiny bit, and of course it's going to be slower, right? So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, stop. So I'm sure you can do it better than I'm doing at home. So you should find when you average about 11.4 seconds. I don't have to put the second here because I have the second there, but it's fine. And then I increase again. So you see now it's going to be super slow. So almost touching the table here. So I'm going to count 10. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Stop. So you find about 12.2 seconds. So you have to stay stop when it's at the lowest point, okay? Maybe I missed that, but I stopped my smartphone when it was at the lowest position. And you see how it's slow now because you have increased the inertia so much. So of course, again, each trial here, you have to do it several times and average out. So now you divide by 10 here, right? So it's easy. So it's going to be, you move the decimal. So 1.05, 1.14, 1.22. So it's just to give you an idea because, of course, my setup is not of great precision. So you square. So you square here, you get about 0.9. Here you get 1.1. Here you get 1.3. And here you get 1.5. So what you see here is that each step, so that's the independent variable. The mass is the independent variable in that equation here. So that's an independent variable here. So each step here of plus 10 gram, that's plus 10 gram. Here you go by 0.2. And then here it's again 0.2. And again it's 0.2. So each step here is 10 grams. And here it's 10 grams. So that means it's a linear relationship between t squared and m. What we usually do is to make a best fit line with a spreadsheet, find the slope, and once you have the slope, that's going to be the slope here, okay? You can find k. Okay, so if the slope I have found here is delta y, so that's going to be your delta y, that's going to be your delta x. So the slope, it's going to be 0.2 seconds square over 10 grams. So I cannot say this is equals to that because I need to have the right unit. So you need to convert the mass here to kilogram. So if I convert the mass to kilogram, I'm going to have a slope is 0.2 over, so you divide by 1,000, 0.01. So the slope is 20. When you divide by 0.01, that means you multiply by 100. So you plug, that's going to be your theoretical slope. So if the slope here, if this is equals to 20, you can solve for k. Okay, so this is equals to 20, and you find that k equals 4 pi squared divided by 20, and you get about 2. The unit is Newton per meter. Okay, so that's not too surprising. It's because it's a very flexible spring, you know, it's not very stiff. So you expect the spring constant to be 2. Once you have calibrated your system, so once you know that here equals 20, if you have an unknown mass, okay, let's say the mass you don't know, you find t squared, so you find this equation, you use that equation to find the unknown mass, okay? So you can put a mass here, you don't know the mass, unknown mass, you find the period, you square it, you use that equation to find the unknown mass. Of course, you can use Hooke's law. So you can use Hooke's law to find K to see if to verify. Okay, so we can use Hooke's law to see if we find about the stem value of K, the spring constant. So you see here, I zero it, right? So the mass of the holder doesn't matter. Here I am at 0. And I'm going to add 20 grams. So that's 10 grams here. 10 grams. And then another 10 grams. So that will be 20 grams. And of course, it's going to stretch, right? Because remember, Hooke's law says that the strain, so the amount by which it has stretched out, is proportional to the stress. And the stress here is the weight. So Hooke's law says that F equals K delta X. That has to be in Newton, and that's going to be in meters. So the force here is, have to convert that to kilograms. So I have 0.02 kilogram, okay, which is 20 grams. 9 times 9.8, so let's say times 10, because anyway, my setup is not very precise. Okay. And by how much it stretched, you see it's about 10 centimeter, okay? It's not very precise. Cannot expect to have a great resolution. It's about 10. So here I'm going to put in meters, so it's going to be 0.1, right? So you have K is 0.2 divided by 0.1, and we get 2. So even though this setup is not, it's not super precise, we still get the same K. Okay, so very easy experiment to do. I bought that online. That's the brand. It's a new brand I have found, and they have relatively cheap material. And no, I'm not sponsored. I just do that for my class. Okay.